So I want to talk a little bit about chemical education research as a possible research topic. So I'd like to start off with this slide just to differentiate between chemical education practice and research. So for practice, really focusing on developing things that you would use in the classroom, but not really involved in the assessment of that approach. So you might write a new lab experiment, you might develop a new classroom module, but you're just focused on creating something to use in the classroom, not investigating does that actually improve student learning. For research, we're trying to measure the effectiveness of a particular implementation or designing specific things to answer a particular research question, why students learn in a particular way. So you might develop a particular experiment or a particular tool to investigate one aspect. Some of the research topics that I've been looking at incorporating environmental data into the curriculum, assessment of the effectiveness of active learning techniques and technology. I'm going to talk about a couple of those to start. So one central project relates to a pedagogical technique that I started to do a little bit of, and that's called flipping the classroom. But in general, I've looked at the implementation of technology. So most of you know that I use clickers in classroom, see me wheeling carts around. So that's a technology that's both used to facilitate student learning and as an assessment tool, a way for me to measure student understanding. So what is a flipped classroom? So the concept of the flipped classroom, the terminology is relatively new. The concept is really not new. Humanities will tell you that they've been flipping the classroom forever because they have students read things and then discuss it in class. So that is not something that we've typically done a lot of in the sciences, particularly in the large lecture classes. So this concept of flipping the classroom in the sciences is to take what's traditionally done in the classroom, which is the dissemination of information, and move that outside of class. So in a standard science class, face-to-face time is spent disseminating information, and then students take that information and they practice that at home. So they do, that's what homework is, take this information and now work with it. And so in the flipped classroom, you take that general information delivery and you move that online. And then in class is well, now let's try and understand how to work with that information. So there are different ways of moving that content online. You could record lectures, you could create podcasts, you could just refer students to already existing instructional videos, Khan Academy, for example. So the class time becomes devoted to active learning techniques, group work, homework exercises. Some implementations focus on really elaborate activities in class, things like problem-based learning. So I did kind of a implementation by necessity last year due to weather. We ended up losing a bunch of classes, so I fell behind in my content coverage, and I decided one way to catch up was to do a partial flipping where I recorded short lectures and moved those online, and then that allowed us to catch up in class, and I could spend a little bit more time going over questions and calculations. So they were always posted the day before the class, and then to try and reinforce the importance of compliance, that students need to actually watch the videos before they came to class, we started off with quicker questions that related to that content. So one, it was to reinforce to students that this is content I'm expecting that you know, but also it allowed me to find out if no one watched the video. Because if I asked a quicker question, everyone got it wrong, go. They didn't watch it, so now I can't assume that they have that knowledge. So I kind of started in week 4, basically when the snow started. So I had a student last year that did some analysis and tried to look at student performance on exam questions relating to different content, whether that content was covered only in the video format, only in lecture, or on both. And the results are kind of all over the place. And for this, because this really wasn't a design study, I was glad to see this initial analysis really just to show that I wasn't doing irreparable harm to the students. So the goal for this really, we just wanted to make sure that the students weren't completely failing on all the content that I had moved online. And so for some of the content, the students actually did better. For some of the content, they didn't do as well. So if we're really going to turn this into a research study, then we'd have to do a lot more detailed error analysis. Are those differences even statistically significant? Compare the scores with student viewing data. So fortunately, with our course website, we can actually track students' viewing of the videos. What is the effect of exam question difficulty? So for example, are there differences in those responses just because certain content is more difficult than other content? And are those results reproducible year to year? Then the other thing that I wanted to do was just talk about two projects that my current senior research students are doing right now. So just a very quick introduction. So one of my students this year is looking at student use of online review session videos. So before each exam in general chemistry, we run a face-to-face review session, but we also record those. We record that review session and then post the videos online. So he's looking at what factors might affect which videos students are more likely to watch. So we've posted the videos in a couple different ways: a full video, so the full 2-hour video in one video, and then also question by question. So the review sessions are set up basically about 20 questions where the students answer. And so the anecdotal information when you talk to people about posting videos is that students won't watch a long video, that they will only watch things 5 to 10 minutes because that's their attention span. So I can tell you that the preliminary analysis is that the video file that gets the most views each review session is the full video. Now the students obviously are not necessarily watching the entire video, but they are going to that one preferentially over the other videos. But all you hear are just anecdotal information. Oh, it needs to be short, or students won't watch it. But I haven't really seen anything in the literature where someone's really looked at it quantitatively. So we want to look at, of the individual questions, which video files are students more likely to watch? Are they more likely to watch a hard question, an easy question, a complex topic, a simple topic? Are they more likely to watch questions that were quantitative? Are they more likely to watch questions that were related to a conceptual question? And then also correlating that viewing to exam performance. So we can take those individual review session questions and relate them to the corresponding exam questions. Do students who watch that video, are they more likely to get that particular question correct? The other project, the project that my other student is working on, is looking at active learning activities that are used in recitation for the chemistry majors class. So these activities have a particular format called POGLE, stands for Process-Oriented Guided Inquiry Learning. And what she's doing is she's looking at exam questions that directly relate to the POGLE activities. And are the students more likely to get the exam questions that relate to the activities? Are they more likely to score well on those questions versus questions that were not related to the activities? She's also looking at in-class clicker questions to see if that's as another way to track student understanding of that particular content. We also have some of these activities that have a climate change focus. And that's an NSF grant that we have to write climate change activities that are used to teach general chemistry. And do we see a difference in student performance relating to content in those climate change activities versus the other activities? So for those specific climate change activities, we have individual 2-question assessments that students take in class after they do that activity as another measure of their understanding of that content. So those activities, those climate change activities, are related to this project where we're writing in collaboration with a bunch of different authors at different universities. We're writing these climate change activities. We have a 5-member authoring team, but 8 total institutions involved, and that project is wrapping up this year. And so that's where I will end. Happy to answer any questions.